Section 10.3, Convergence of Positive Series. The goal of this section is to determine the convergence or divergence of infinite series of the form summation a sub n, where every term a sub n is positive, and we call these positive series. One of the key features of positive series is that if every term is positive, then the nth partial sum s sub n, which is a1 plus a2 plus down to a sub n, can be visualized as the sum of areas of rectangles by just visualizing the base of the first rectangle as 1, the height is a1, so the area is a1, and similarly from 1 to 2, with a height of a2 gives us an area of a2. So the sum of these a1, a2 down to an is really just the sum of these rectangles, and this is a powerful tool that leads very quickly to a very nice theorem for testing convergence and divergence of certain infinite series. And this is called the integral test. The integral test says let a sub n equal f of n, so we want to track the function that our general term a sub n is dictating, where f here is a positive, decreasing, and continuous function of x for x greater than or equal to 1, and the 1 here isn't so important. It could be for x greater than or equal to any a that you want to. But let's just say with 1. And then the integral test says the following. If the integral from 1 to infinity of f of x dx converges, then the infinite series converges, of the a sub n's converges. If the integral from 1 to infinity of f of x dx diverges, then the infinite sum, the infinite series of the a sub n, diverges also. So what it says is that the convergence or divergence of this series goes hand in hand with the convergence or divergence of this associated improper integral. So let's look at a concrete example to see how this can be applied. Example 1. Does the sum from n equals 1 to infinity of 1 over n converge or diverge? It turns out that this series is kind of a famous series. It's called the harmonic series, and we'll talk about this more in just a little bit. Let's just, for now, it's a series that we want to analyze the convergence or divergence of using the integral test. So here we need to set up what our an is and what our f is, and then we want to check the hypotheses of the theorem and then see what the improper integral tells us. So here our a sub n's is our f of n, which is 1 over n, so our f of x is 1 over x. We want to check, remember the hypotheses are that f has to be a positive, decreasing, and continuous function on some interval from, say, a to infinity. So here our function is certainly positive on 1 to infinity. It's decreasing on 1 to infinity, and it's continuous on 1 to infinity. So then, by the integral test, we just need to check the integral from 1 to infinity of f of x dx, so 1 over x dx. This is a familiar improper integral to us. This is a p integral of the first kind with p equals 1, so we know that it diverges. Since this improper integral diverges, by the integral test, the sum from n equals 1 to infinity of 1 over n diverges. So if the improper integral diverges, the infinite series diverges also. So this leads us to the topic of p-series. And if you remember p integrals of the first kind from what we studied before, they had the form integral from 1 to infinity of 1 over x to the p dx. Remember that they converge when p is greater than 1, and they diverge when p is less than or equal to 1. So if you recall this, that motivates the next topic, which is the so-called p-series, and they look like summation n equals 1 to infinity of 1 over n to the p for some power p. We call these p-series, and by the integral test, we know that this infinite series either converges or diverges according to the convergence or divergence of this improper integral, and since we know when this improper integral converges, we can immediately deduce when the p-series converge or diverge. And so by the integral test, a p-series is going to converge when p is greater than 1, and it's going to diverge when p is less than or equal to 1, because that's exactly what the associated p integral does, the p integral of the first kind does. So this leads us to, let's look at another couple of examples here. If you had the sum of from n equals 1 to infinity of 1 over the square root of n, and you just want to know the convergence or divergence here, you can rewrite this as the sum from n equals 1 to infinity of 1 over n to the 1/2. This is now, we spot this as a p-series with a p equals 1/2, which is less than 1, so this series diverges. Similarly, the sum from n equals 1 to infinity of 1 over n squared, We spot this as a p-series with a p equals 2, which is greater than 1, therefore this series converges. Note that the harmonic series that we just had in example 1, the sum from n equals 1 to infinity of 1 over n, is a p-series with p equals 1, and just like we saw with p integrals when p was equal to 1, these form the boundary between convergence and divergence for p-series. P equals 1 is the hard boundary between whether the p-series converges or the p-series diverges. And exactly at p equals 1, we get divergence. Now, another test that we want to be able to use is called the direct comparison test. And so the reason we have these various tests is maybe the hypotheses of the integral test don't apply in a certain situation. So we like to have as many tools and as many options as possible. Maybe it's doable by the integral test, but it would be much easier to do by another method. So we'd like to have as many tests to determine convergence or divergence as we can. So another one that is reminiscent of what we studied with improper integrals when we had a comparison test there is the so-called direct comparison test for infinite series. And it goes like this. Assume that there exists some integer m positive such that 0 is less than or equal to a sub n is less than or equal to b sub n for n greater than or equal to m. All this says is that you have a sub n and b sub n. They're greater than or equal to 0, and a sub n is underneath b sub n is less than or equal to b sub n. And it may not be always true, but it's at least eventually true if you go far enough out in the sequence that this inequality is going to hold. And so this says if the sum of the b sub n's converges, then the sum of the a sub n also converges. And if the sum of the a sub n diverges, then the sum of the b sub n diverges also. Again, this is reminiscent of the comparison test with improper integrals. And the idea there was if you have everything that's positive or at least non-negative, and you have this sort of sandwiching effect, if this sum converges, if the sum of these converges, then the sum of these must be less than or equal to the sum of these, and they're all positive, so this must converge also. On the other hand, if these are bigger than these, then the sum of these must be bigger than the sum of these, and so if the sum of these diverges, the sum of these diverge also. For a careful proof, see the text, but this definitely reminds us of the comparison test for improper integrals. Let's look at an example. Example 3. Determine the convergence or divergence of the sum from n equals 1 to infinity of 1 over the cube root of n times 2 to the n. Okay, so if we just look at this, we may think, okay, well, do we think that this series converges or diverges? What test might we use here? Well, since we're trying to give an example of the direct comparison, we should be thinking if we take this part of the sum, the general term, the a sub n, we should look at the a sub n and see if we can do a direct comparison with, in the terms of an inequality that's true, that is useful to us in the sense that we know something about the convergence or divergence of the quantity that we're comparing this to. So for example, we can look at this and we can see for n greater than or equal to 1, these are all greater than 0. So we know that this is true. And now to move from here to here, you might say, well, if I look at this quotient, if I remove, this is certainly a positive term and this is a positive term and it's a term that's greater than 1, for n greater than or equal to 1, you could say, well, if I erase this term, then I have removed something that's larger than 1 from the denominator, so the quotient must be getting bigger, and that is true. That's a direct comparison. And now let's see if it's useful, because if this is true, this inequality is true, and the reason we like this is we visualize this pretty quickly as a 1 over n to the 1/3, so this is a p-series with a p equals 1/3. So it's something that we know about the convergence or divergence of once we sum it. So if this direct comparison is true, then we know that if we sum this, the sum of these must be less than or equal to the sum of these. And like we said, the sum of these we can rewrite as this. This is a p-series with p equals 1/3 and it diverges. So if you notice, we've written down totally true things here, but it's not useful because look at what happens. All that we can say about the series we're interested in is that it's less than or equal to something that's known to diverge. The reason I included this example is oftentimes we can make direct comparisons and they are true comparisons, but they're not helpful in determining convergence or divergence. And so I wanted you to see what that feels like because it could easily happen to you. It doesn't necessarily mean that you did anything wrong. So not only do we need a comparison, but we need a comparison to where we know, for example, if we're thinking of our a sub n's, the sum of our a sub n's as the series that we're trying to, for example, show convergence of, then we need the sum of the b sub n's to converge. On the other hand, if we're thinking that our b sub n's are the sum of our b sub n's, we want to diverge, or we suspect that it diverges, then we want to show that that's larger than something that is known to diverge. So we have to make sure that we get not only a true direct comparison, but one that's useful. So if we go back and start over, we try again, we could take our same function that we know is greater than 0, and instead of dropping this term that's greater than or equal to 1, why don't we drop this term that's greater than or equal to 1? And so now we still have an inequality that's true, a direct comparison that's true, and let's see if it's helpful. So if this inequality is true, and it is, then the sum of these must be less than or equal to the sum of these. And if you notice, we can rewrite this as this. And this is a geometric series with a geometric ratio of 1/2, which is an absolute value less than 1. So this converges. So now think about what we just said. This infinite series that we're interested in is less than or equal to this infinite series that we know converges. And because it's smaller, and while still being positive, it's smaller than something that's known to converge, then by the direct comparison test, our given series also converges. So this is a great example seeing how you can make a true direct comparison, and one of them is helpful and one of them is not. And so we always want to strive to have helpful comparisons. And one of the key features that you need to remember about the direct comparison test is, again, the a sub n's and the b sub n's both need to be greater than or equal to 0. Let's look at another example. Example 4. Does the sum from n equals 2 to infinity of 1 over n times the ln of n quantity squared, does it converge or diverge? Well, we're working with the direct comparison test, so it seems like we want to make a direct comparison. And one of the things we need to realize is oftentimes when you have quotients like this, you're looking to drop something from the quotient, from the denominator of the quotient, assuming that that thing is greater than or equal to 1 in order to make the quotient larger. So here first we notice that these are all positive, okay, for n greater than 2, n equals greater than or equal to 2. So these are all positive. And now notice, since the ln of n quantity squared is greater than 1 when n is greater than 2, then if we drop this term, we will have been removing a term that's greater than 1 from the denominator, so we must be making the quotient larger. So we do have a direct comparison. Let's see if it's helpful. If this direct comparison is true, and it is, then we know that the sum of these is less than the sum of these. And now, do we know something about this series? Yes, this is the harmonic series, and it diverges. So notice, again, we have a true but unhelpful comparison. This is often a frustrating thing for students, and then they think, well, what else am I supposed to try? But this just happens in real life examples. We have a direct comparison that's true, but we don't have something that's helpful in terms of convergence or divergence. And so the moral of the story, the reason I included this example is be flexible. You don't have to use the direct comparison test. You have all of your tests at your disposal. And so this is a great example to where maybe it's not so easy to do a direct comparison test. Instead, we'll pivot and use the integral test. This gives us another look at an integral test example. So we have this one, and so our a sub n's is f of n, which is 1 over n ln of n quantity squared. Let's do the checks, and you definitely need to show all of this work. You need to show your reasoning. Is f greater than 0? Yes. Is f decreasing? Yes. You could, if you look at what this graph looks like, or I think what's simpler is just notice the denominator, I have 1 over, and then this denominator is growing. This is a growing function, and so since the denominator is growing and the numerator is staying the same, the quotient is decreasing. And lastly, is f continuous for x greater than or equal to 2? Yes, this is a continuous function when x is greater than or equal to 2. So we have the green light to use the integral test. We should compute the improper integral. Notice this one starts at 2, so this starts at 2. We need to compute this improper integral. We'll go through this kind of quickly. We know that we write this improper integral of the first kind as a limit of proper integrals. We perform a u substitution, including changing the limits to get this integral. We anti-differentiate, evaluate between limits. Now we take the limit as r goes to infinity. Well, remember, ln of r is going to infinity, so this term is going to 0. So this gives us a 1 over ln of 2. There isn't anything sacred about this number. The key thing, if you go back and you look at the integral test, the key thing is, does this integral converge or diverge? And what we found is that this integral equals this finite number, therefore it converges. The important thing is that it's less than infinity. So this improper integral converges. So by the integral test, the series we were interested in converges also. So sometimes the integral test isn't applicable and a useful direct comparison isn't apparent. Maybe that happened in the last example, or there could be more complicated examples. And so are there any other methods that we can use? What else can we do? And this leads us to not the direct comparison test, but the limit comparison test. The limit comparison test says, let a sub n and b sub n be positive sequences, and so assume that the following limit exists. We want to compute the limit as n goes to infinity of an over bn, and let's get that limit. And it says if that limit is positive and finite, then the sum of the a sub n converges if and only if the sum of the b sub n converges. So this is far and away the most common situation that you get. You compute the limit of this quotient, and you just see what that limit comes out to. If it comes out to be positive but finite, then whatever one series does, the other series does. If one converges, the other converges. If one diverges, the other diverges. On the other hand, if this limit comes out to be infinity, then it's a little bit trickier. If the L is infinity and the sum of the a sub n converges, then the sum of the b sub n converges. On the flip side, if L is 0 and the sum of the b sub n converges, then the sum of the a sub n converges. Again, see the text for the proof, but we're just going to work through some examples. So here, in example 5, does the sum from n equals 2 to infinity of n over n squared minus n plus 1 converge or diverge? Now the way we're going to get started, and this is part of the creativity that comes with every one of these has some kind of creativity. I think the integral test is the most straightforward, except you need to be able to compute the integral. And before you embark on using the integral test, you really need to look at that and eyeball it and see if you think that the associated improper integral is computable. On the other hand, when you have a direct comparison test, the artistic part of it is trying to find the useful direct comparison. In this test, with the limit comparison test, the art form is, hey, if I have this sum, then this might be my a sub n or my b sub n. Usually you let this be your a sub n. And then the question is, what am I going to take to be my b sub n? How do I just pull the b sub n out of thin air? Well, I'll give you a few pointers of how to do this. And one of the most basic things that you can do is what's called a dominant term analysis, as just to get a candidate b sub n. I'm not saying that this is the best b sub n. I'm not saying that this b sub n will always work, but it's one that you can at least give a try to, and if it works, and you can use the limit comparison test with it, then you just go with it. So what I mean by a dominant term analysis is take the a sub n, I'm going to think of this as my a sub n, and then I'm going to think about what happens when n goes to infinity. As n goes to infinity, then I just think about what's the dominant term here, the highest order term. The fastest growing term here is an n. The fastest growing term here is the n squared. So these terms, I'm not saying these are equal. I'm saying that what's really, as n gets really, really large in the limit, this is the dominant term and what really matters for really large n. So I'm saying that this quotient is approximately the same as this quotient, not always, but as n goes to infinity. This simplifies very nicely to 1 over n. And usually when you do a dominant, a good thing to try is do a dominant term analysis. And if this is fairly clean and you get whatever you get here that is much simpler than what you have here, take this to be your b sub n. At least give that a try. So I'll take my a sub n to be the original general term, my b sub n to be the general term that I got through a dominant term analysis, and then I'll take the limit of the quotient of those two things. So this gives me the limit of this over this. After a little bit of algebra, just invert and multiply. I need to take this limit. I feel like I'm in familiar territory now because after I simplify this, notice this is an infinity over infinity indeterminate form. I'll just use L'Hopital's rule, Or maybe you use the theorem that comes from L'Hopital's rule that says that the degree of the numerator is the same as the degree of the denominator, so the limit is the ratio of the leading coefficients. However you get at it, we can find this limit rather quickly. This limit is 1. The key thing about 1 from the limit comparison test, our L is 1. The important thing is that that's positive and finite, and so by the limit comparison test, it says the sum of the a sub n's and the sum of the b sub n's will do the same thing. They either both converge or they both diverge. And the important thing here is I know what the sum of the b sub n's does. And so since the sum of the b sub n diverges and the limit comparison test says the sum of the a sub n's does the same thing, then our original series, our given series must diverge also. So it is important when you go to do this an and bn, when you pick your bn, it needs to be something that you have a feel for whether it converges or diverges. If you pick a bn that's so complicated that you're not sure if it converges or diverges, and then you have to use another test, you're just picking a bn that's too complicated, and it's not super helpful. How about another example? Let's determine the convergence or divergence of the sum from n equals 1 to infinity of 1 over the square root of n plus ln of n. Again, we'll practice with a dominant term analysis. So as n goes to infinity, our original a sub n here, we can just look at the dominant term in the numerator as 1. The dominant term in the denominator, remember from our work with L'Hopital's rule that n grows faster than ln of n. And so this is the dominant term. It's not because it's first, it's because it grows faster. So we keep the n here. We'll leave the square root, so this is an n to the 1/2. So I'll pick this to be my b sub n. And the good news is, thinking ahead, I know what the sum of these does, because when I sum these from n equals 1 to infinity, I get a p series with p equals 1/2, and I have a good idea what that infinite sum does. But before we get to that point, here's my a sub n, here's my b sub n through a dominant term analysis. I'll define those there. We'll look at the limit as n goes to infinity of the a n over the b n's, which is this limit. After a little bit of algebra, we notice that this is an infinity, so we'll rewrite this as a square root of n, and then we have a square root of n over the square root of n plus ln of n, so we can write that as the square root of one big quotient, n over n plus ln of n. This is an infinity over infinity indeterminate form, and if you just want to brute force calculate it with L'Hopital's rule, go right ahead, but we can also use our continuity theorem from 10.1, and we can work smart instead of hard and just say, well, hold on a second, this is an infinity over infinity form. So before I use L'Hopital's rule, why don't I just use continuity, which said I can slide this limit inside this continuous function. Since the square root is continuous, I can slide the action of this limit inside the square root. And now look at what's in the blue box. That is a little much easier to do L'Hopital's rule problem. Here it is. That's an infinity over infinity form, so by L'Hopital's rule, I get this. This term goes to 0, so the limit is 1. So I get a 1 inside the square root, which gives me a 1. There isn't anything sacred about the 1. What's important is that our L, this is the value of our capital L, it's greater than 0 and it's finite. So the good news is the sum of the a sub n's and the sum of the b sub n's, whatever one does, the other does in terms of convergence and divergence. And that's great news because I know that the sum of the b sub n's was a p series with p equals 1/2, which is less than 1, so it diverges. So that says that my given series diverges also by the limit comparison test. Be sure when you're doing this, you show that you've checked all the hypotheses, and be sure to refer to the test by name so I can know what test you're doing when you're making your argument. So example 7. Does the sum from n equals 0 to infinity of 2 to the n over n times 3 to the n converge or diverge? This one looks a little different. I did this purposefully just to give you a diversity of examples. So again, why don't we try a dominant term analysis? If we have, as n goes to infinity, the dominant term here is 2 to the n. The dominant term here is the exponential. And so now we can write this 2 to the n over 3 to the n as a 2 over 3 all to the n. And so now if this is going to be my a-n's, I'll take this to be my b-n's. Notice that all of these are positive, so it passes the criteria for the limit comparison test. I'll form the limit of the quotient. And after we do this and a little bit of algebra, look what nice cancellation happens. The 2 to the n's cancel, the 3 to the n's cancel. We're left with the limit as n goes to infinity of 1 over n, which goes to 0. I wanted to give you a look of something where you got one of the other cases of the limit comparison test, where the L wasn't always positive and finite. And so what this happens here is we get an L of 0. And then what the theorem says, if we go back and look, when our L is 0, and what the theorem says is if your L is 0 and the sum of the B sub n converges, then the sum of the A sub n converges. So we want to go back and we want to see what happens to the sum of the B sub n's. Well, the sum of our B sub n's was the sum from n equals 0 to infinity of 2/3 to the n, and that's a geometric series with r equals 2/3, which has an absolute value less than 1, and so it converges. And therefore, by that part of the limit comparison test, the given series converges also.